So those are the two equations we need to combine. So we will just substitute this in for L, and we get C equals 60W plus 120,000 over W. Or, to make it easier to differentiate, since that's what we're going to have to do, let's rewrite it as 60W plus 120,000 W to the minus 1. So step 4 is to use calculus methods to find the extrema. Well, you know what that means. We need to find the derivative, find the critical numbers, and work from there. So C prime is equal to 60. We're differentiating with respect to W. It's 60 minus 120,000 W to the minus 2. Or 60 minus 120,000 over W squared. So we need to find critical numbers. There are two ways to find critical numbers. We can find where the derivative is undefined. There is such a place at W equals 0, but of course W equals 0 will not give us an area of 6,000 square meters. So we can eliminate that possibility. So the other choice is to set this equal to 0 and solve the resulting equation. Alright, so 60 over 1 equals 120,000 over W squared. That tells us that 60W squared equals 120,000. And to me that looks like it's going to be 2,000. W squared equals 2,000. Alright, so W then is equal to the square root of 2,000. Well, let's see. That's going to be the square root of 2 times the square root of, maybe it's the square root of 20 times the square root of 100. That would be the square root of 4 times the square root of 100 times the square root of 5. So to me that looks like it's going to be 20 times the square root of 5. And that's approximately 44.7. Alright. The last thing we need to do is answer the question and show that we actually get a minimum. Answer the question as originally posed and show we get, in this case, a minimum. Alright, so the question was, find the outside dimensions that minimize the cost. So we know the width, now we need to find the length. So the length is 6,000 over W. And let's see, we can take out a common factor of 10, and I believe that's going to be 300 over the square root of 5. And let's see, let's rationalize that denominator. That's 300 times the square root of 5 over 5, which is 60 times the square root of 5, which sounds like it's 3 times what we have up here. So we get about 134.2 meters for the length. So now we need to show that we get a minimum, and we can do that with either the second derivative test or the first derivative test. I think the second derivative test will work in this particular example, so let's try that. The original first derivative was 60,000 minus 120,000 W to the minus 2. If we differentiate this, we'll get 0 plus 240,000 W to the minus 3. Which I'm going to write as 240,000 over W cubed. Now, W is positive, so this is going to be positive for our value of W. So that means that the graph is concave up, and we get a minimum by the second derivative test.